Chloride stress corrosion cracking or Cl-SCC as a part of environment-assisted cracking. Description of chloride stress corrosion cracking based on API 571, surface-initiated cracks caused by environmental cracking of 300 series SS and some nickel-base alloys under the combined action of tensile stress, temperature, and an aqueous chloride environment. The presence of dissolved oxygen increases propensity for cracking. Here's a detailed description of chloride stress corrosion cracking or Cl-SCC damage overview. Chloride stress corrosion cracking is a form of environmentally assisted cracking that occurs in susceptible metallic materials, predominantly stainless steels and some high-strength alloys, when exposed to chloride-rich environments under tensile stress. It results in the sudden and often catastrophic failure of components, primarily in marine or chloride-contaminated environments. Mechanism of chloride stress corrosion cracking or Cl-SCC. Cl-SCC is a complex interplay between mechanical stress, environmental factors, and material susceptibility. The process involves several stages. Number 1 is initiation. The process begins with the presence of tensile stress, either residual stress from manufacturing or operational stress, chloride ions, Cl, abundant in seawater, de-icing salts, or other chloride-containing solutions, penetrate the protective passive oxide film on the metal surface. This penetration leads to localized breakdown or thinning of the passive film, creating microcracks or corrosion pits. Process mechanism number 2 is propagation. Once initiated, the crack propagates incrementally along the grain boundaries or through the metal matrix. Chloride ions concentrate at the crack tip, exacerbating localized corrosion. The high concentration of chloride ions destabilizes the passive film further, facilitating crack growth. Mechanical tensile stress works synergistically with electrochemical reactions, encouraging the crack to extend deeper into the material. Process mechanism number 3 is crack growth and failure. The crack advances incrementally, often with a brittle appearance despite the ductile nature of the material. The process can be rapid or slow, depending on environmental conditions and stress levels. Ultimately, the crack may reach a critical size leading to sudden fracture of the component. Material susceptibility. Austenitic stainless steels, such as 304, 316, are particularly vulnerable, especially in chloride environments. High-strength, low-alloy steels and nickel-based alloys can also be prone. The susceptibility is influenced by factors such as alloy composition, microstructure, residual stresses, and the presence of protective oxide films. Environmental factors. Chloride concentration. Higher chloride levels increase risk. Temperature. Elevated temperatures accelerate corrosion processes. pH. Slightly alkaline to neutral pH conditions are common, but the process can occur over a range. Presence of other ions or contaminants can influence corrosion dynamics. Stress factors. Tensile stress can be residual, from welding or fabrication, or operational, applied loads. Stress intensity factors exceeding certain thresholds. Promote crack initiation and propagation. Chloride stress corrosion cracking is a dangerous phenomenon that combines mechanical stress and chloride-induced electrochemical attack, leading to cracking that can compromise structural integrity. Its understanding involves considering material susceptibility, environmental conditions, and stress levels, with appropriate preventative measures critical for safety and longevity of affected components. Chloride stress corrosion cracking or Cl-SCC affected materials based on API 571, number A, all 300 series SS are highly susceptible. Number B, duplex stainless steels are more resistant. Number C, nickel-base alloys are highly resistant, but not immune. Here's a comprehensive and detailed explanation of the materials affected by chloride stress corrosion cracking or Cl-SCC overview. Cl-SCC primarily impacts metals and alloys that possess certain electrochemical and microstructural characteristics, making them susceptible to chloride-induced cracking under tensile stress. The susceptibility varies among different materials based on their composition, microstructure, surface condition, and environmental exposure. Here's a comprehensive and detailed explanation of the materials affected by chloride stress corrosion cracking or Cl-SCC. Number 1 is austenitic stainless steels. The most common materials affected by Cl-SCC, typically used in environments prone to chloride exposure such as marine, chemical processing, and desalination plants. Examples of austenitic stainless steels: Type 304 stainless steel, contains approximately 18% chromium and 8% nickel. Type 316 stainless steel, similar to 304 but with added molybdenum up to 2 to 3% for increased corrosion resistance. Susceptibility factors of austenitic stainless steels: passive film breakdown. The chromium-rich oxide film that passivates stainless steel can be locally disrupted by chlorides. Microstructure, sensitization, chromium carbides precipitating at grain boundaries, enhances susceptibility. Residual stresses, welding, forming, or machining processes induce residual tensile stresses that facilitate crack initiation. High temperatures, elevated temperatures, above 60 degrees Celsius, increase chloride ion penetration and accelerate SCC. Additional notes: austenitic steels are generally resistant to uniform corrosion but vulnerable to localized attack like SCC in chloride environments. Number 2 of the materials affected by chloride stress corrosion cracking or Cl-SCC is high-strength low-alloy steels or HSLA and carbon steels. Some high-strength steels, especially those with significant tensile stresses, are susceptible under specific conditions. For examples, certain quenched and tempered steels used in structural and pipeline applications. High-strength low-alloy steels or HSLA and carbon steel susceptibility factors includes residual or applied stress. High tensile stresses are critical. Microstructural features: fine-grained microstructures or coarse grains can influence vulnerability. Surface condition: rough or damaged surfaces with microdefects promote initiation. Generally, less susceptible than stainless steels but can still experience Cl-SCC if stressed and in chloride environments. Number 3 of the materials affected by chloride stress corrosion cracking or Cl-SCC is nickel and nickel-based alloys. Some nickel alloys are resistant, but certain compositions are vulnerable, especially at elevated temperatures. For examples, Inconel alloys, such as Inconel 600, 625 resistance varies. Inconel 600 can be susceptible, and Hastelloy resistance depends on specific alloy composition. Nickel and nickel-based alloys susceptibility factors includes alloying elements influence passivity and chloride resistance. Microstructure and residual stresses also play roles. Number 4 of the materials affected by chloride stress corrosion cracking or Cl-SCC is titanium and titanium alloys, generally resistant to chloride environments due to stable oxide films. However, certain conditions or alloy compositions can lead to SCC. Other materials affected by chloride stress corrosion cracking or Cl-SCC includes aluminum alloys, usually resistant but can be susceptible under certain conditions involving chlorides and tensile stress. Copper and copper alloys, typically resistant but can experience localized corrosion or SCC under specific circumstances. Factors influencing material susceptibility includes microstructure. Sensitized microstructures with grain boundary precipitates increase susceptibility. Surface condition: rough, damaged, or contaminated surfaces promote initiation. Residual stresses: welding, forming, or machining induce tensile stresses. Temperature: elevated temperatures can accelerate chloride penetration and SCC. Chloride concentration: higher chloride levels magnify risk. Environmental pH: near neutral to alkaline environments are common in chloride SCC scenarios. Cl-SCC primarily affects susceptible stainless steels, especially austenitic grades like 304 and 316, due to their passive film characteristics and microstructural features. High-strength steels, certain nickel alloys, and other metals can also be impacted under specific conditions involving tensile stresses and chloride exposure. Understanding material susceptibility is crucial for selecting appropriate alloys, applying protective measures, and implementing effective inspection routines to prevent catastrophic failures. Chloride stress corrosion cracking or Cl-SCC critical factors based on API 571, Number A, chloride content, pH, temperature, stress, presence of oxygen and alloy composition are critical factors. Number B, increasing temperatures increase the susceptibility to cracking. Number C, increasing levels of chloride increase the likelihood of cracking. Number D, no practical lower limit for chlorides exists because there is always a potential for chlorides to concentrate. Number E, heat transfer conditions significantly increase cracking susceptibility because they allow chlorides to concentrate. Alternate exposures to wet-dry conditions or steam and water are also conducive to cracking. Number F, SCC usually occurs at pH values above 2. At lower pH values, uniform corrosion generally predominates. SCC tendency decreases toward the alkaline pH region. Number G, cracking usually occurs at metal temperatures above about 140 of 60 OC, although exceptions can be found at lower temperatures. Number H, stress may be applied or residual. Highly stressed or cold-worked components, such as expansion bellows, are highly susceptible to cracking. Number I, oxygen dissolved in the water normally accelerates SCC, but it is not clear whether there is an oxygen concentration threshold below which chloride SCC is impossible. Number J, nickel content of the alloy has a major effect on resistance. The greatest susceptibility is at a nickel content of 8% to 12%. Alloys with nickel contents above 35% are highly resistant and alloys above 45% are nearly immune. Number K, low nickel stainless steels, such as the duplex, ferrite austenite, stainless steels, have improved resistance over the 300 series SS but are not immune. Number L, carbon steels, low alloy steels and 400 series SS are not susceptible to Cl-SCC. Here's a comprehensive, detailed explanation of the critical factors of chloride stress corrosion cracking or Cl-SCC damage. Cl-SCC is a multifaceted phenomenon where environmental, material, and mechanical factors interact to initiate and propagate cracks. The severity and likelihood of Cl-SCC depend on several critical factors, each playing a pivotal role in the process. Understanding these factors helps in predicting, preventing, and mitigating SCC-related failures. The critical factors of chloride stress corrosion cracking or Cl-SCC damage. Number 1 is chloride ion concentration. Chloride ions, Cl, are the primary corrosive species involved in Cl-SCC. The concentration of chloride ions at the metal surface directly influences the stability of the passive film and crack initiation. Details of chloride ion concentration: high chloride levels, such as seawater, de-icing salts, significantly increase SCC risk. Even low concentrations can cause SCC if other critical factors are present. Chloride ions penetrate the passive oxide film, leading to localized breakdown. Implications of chloride ion concentration: environments with elevated chloride concentrations, such as marine settings or industrial processes involving chlorides, are more prone to SCC. Number 2 of the critical factors of chloride stress corrosion cracking or Cl-SCC damage is material susceptibility. Not all materials are equally vulnerable. Susceptibility depends on microstructure, composition, and condition. Details of material susceptibility includes austenitic stainless steels, especially types 304 and 316 are highly susceptible. Microstructure: sensitized microstructures with grain boundary precipitates or carbide segregation increase vulnerability. Alloy composition: elements such as molybdenum enhance resistance, lack thereof can increase susceptibility. Surface condition: roughness, surface defects, or prior damage can serve as initiation sites. Implications of material susceptibility: selection of appropriate alloys and controlling microstructure, for example post-weld heat treatment, are crucial. Number 3 of the critical factors of chloride stress corrosion cracking or Cl-SCC damage is applied or residual tensile stress. Description of residual tensile stress is a driving force for crack initiation and propagation. Details of residual tensile stress: operational stresses include external loads, thermal expansion, or pressure. Stress intensity factor or K: when stress exceeds a critical threshold, cracks can initiate and grow. Implications of residual tensile stress: stress reduction techniques, such as stress relief annealing, are effective in mitigating SCC risk. Number 4 of the critical factors of chloride stress corrosion cracking or Cl-SCC damage is microstructure and grain boundary characteristics. Microstructural features influence crack initiation and propagation. Details of microstructure and grain boundary characteristics. Sensitized microstructure. Carbide precipitation at grain boundaries leads to chromium depletion, weakening the passive film. Grain size. Fine grains may resist crack propagation better, but microstructural heterogeneities can be detrimental. Inclusions and microdefects. Non-metallic inclusions or voids act as stress concentrators. Implications of microstructure and grain boundary characteristics. Microstructural control through heat treatment or alloying reduces susceptibility. Number 5 of the critical factors of chloride stress corrosion cracking or Cl-SCC damage is environmental factors, temperature, pH, and presence of other ions. The environment plays a critical role in SCC susceptibility. Details of environmental factors, temperature, pH, and presence of other ions. Includes, temperature. Elevated temperatures, above 60 degrees Celsius, accelerate chloride diffusion and corrosion reactions. pH, near neutral to slightly alkaline environments are common. Extreme pH values tend to inhibit or change corrosion behavior. Oxygen availability, affects electrochemical reactions at the crack tip. Presence of other ions, sulfates, nitrates, or other species can influence corrosion dynamics. Implications of environmental factors, temperature, pH, and presence of other ions. Maintaining controlled environmental conditions can help prevent Cl-SCC. Number 6 of the critical factors of chloride stress corrosion cracking or Cl-SCC damage is film stability and breakdown. The integrity of the passive oxide film is essential for corrosion resistance. Details of film stability and breakdown. Chlorides destabilize and locally disrupt the passive film, creating initiation sites. Repeated or sustained breakdown leads to crack initiation. The film's ability to reform after disruption influences SCC progression. Implications of film stability and breakdown. Materials with inherently stable passive films or protective coatings are more resistant. Number 7 of the critical factors of chloride stress corrosion cracking or Cl-SCC damage is time and duration of exposure. The duration of exposure to chloride-rich, stressed environments influences the development of SCC. Details of time and duration of exposure. Longer exposure times increase the likelihood of initiation and crack growth. Short-term environments may not cause significant damage unless initial conditions are severe. Implications of time and duration of exposure. Monitoring and timely inspection are vital in high-risk environments. Number 8 of the critical factors of chloride stress corrosion cracking or Cl-SCC damage is operational and mechanical conditions. External factors such as pressure, flow conditions, and cyclic loading influence SCC. Details of operational and mechanical conditions. Flow velocity. High flow rates can increase chloride transport to the surface. Pressure. Elevated pressures can promote crack propagation. Cyclic stresses. Fatigue loading combined with chloride exposure accelerates SCC. Implications of operational and mechanical conditions. Design considerations should minimize stress concentrations and flow-induced erosion. Number 9 of the critical factors of chloride stress corrosion cracking or Cl-SCC damage is presence of residual stresses and manufacturing defects. Manufacturing processes often leave residual stresses that predispose materials to SCC. Details of presence of residual stresses and manufacturing defects includes welding, bending, or forming can introduce tensile residual stresses. Surface defects such as cracks, pits, or inclusions act as initiation sites. Implications of presence of residual stresses and manufacturing defects. Proper stress relief treatments and surface inspections are essential. The development and propagation of chloride stress corrosion cracking depend on a combination of these critical factors. Effective prevention involves controlling environmental exposure, reducing residual and operational stresses, selecting resistant materials, and maintaining proper microstructural conditions. Critical factors of chloride stress corrosion cracking or Cl-SCC damage. Affected units or equipment based on API 571, Number A. All 300 series SS piping and pressure vessel components in any process units are susceptible to Cl-SCC. Number B. Cracking has occurred in water-cooled condensers and in the process side of crude tower overhead condensers. Number C, drains in hydroprocessing units are susceptible to cracking during startup/shutdown if not properly purged. Number D, bellows and instrument tubing, particularly those associated with hydrogen recycle streams contaminated with chlorides, can be affected. Number E, external Cl-SCC has also been a problem on insulated surfaces when insulation gets wet. Number F, cracking has occurred in boiler drain lines. Here's a detailed overview of the units or equipment affected by chloride stress corrosion cracking or Cl-SCC overview. Cl-SCC can compromise a wide range of industrial units and equipment, especially those operating in chloride-rich environments under tensile stress. Its occurrence can lead to catastrophic failures, operational downtime, and significant repair costs. The susceptibility depends on the operational conditions, material selection, and environmental exposure. Here's a detailed overview of the units or equipment affected by chloride stress corrosion cracking or Cl-SCC. Number 1 is pipelines. Description: steel pipelines transporting fluids, especially in marine or brackish water environments, are highly vulnerable. Cl-SCC can occur in both onshore and offshore pipelines. Pipelines details: onshore pipelines, exposed to de-icing salts, road salts, or contaminated soils; offshore pipelines, constant exposure to seawater, high chloride concentrations, and residual stresses from welding or installation; failure mode, cracks initiate at welds, bends, or areas with residual tensile stresses and propagate rapidly. Number 2 of the units or equipment affected by chloride stress corrosion cracking or Cl-SCC is heat exchangers. Description: components such as tubes, shells, and headers within heat exchangers are susceptible, especially where chloride-containing cooling water is used. Heat exchangers details: tube sheets and tubes. Thin-walled tubes are prone to SCC at welds and stress concentration points. Impacts: cracks can cause leaks, reducing heat transfer efficiency and risking contamination. Number 3 of the units or equipment affected by chloride stress corrosion cracking or Cl-SCC is pressure vessels and reactors. Description: used in chemical and petrochemical industries, often in chloride-rich environments. Pressure vessels and reactors details: shells and heads. Under tensile stress from internal pressure, these components can develop SCC. Welded joints, areas with residual stresses are particularly at risk. Failure consequences: rupture leading to leaks or explosion hazards. Number 4 of the units or equipment affected by chloride stress corrosion cracking or Cl-SCC is chemical processing equipment. Description: equipment such as reactors, mixers, and piping in chemical plants handling chloride-containing substances. Chemical processing equipment details: reactors and storage tanks, particularly if made of susceptible stainless steels or carbon steels. Impact: cracks can lead to leaks, contamination, or process upsets. Number 5 of the units or equipment affected by chloride stress corrosion cracking or Cl-SCC is offshore and marine structures. Description: includes platforms, piers, and other structural components exposed to seawater. Offshore and marine structures details: structural beams, girders, and supports, subjected to tensile stresses from loads and environmental forces. Welded joints, common sites for SCC initiation. Risks: structural failure, safety hazards, and costly repairs. Number 6 of the units or equipment affected by chloride stress corrosion cracking or Cl-SCC is cooling water systems. Description: components of cooling water circuits, such as pumps, channels, and piping, are often exposed to chloride-laden water. Cooling water systems details: piping and valves, especially in power plants, where seawater or brackish water is used. Impacts: cracks can lead to leaks, system failures, or shutdowns. Number 7 of the units or equipment affected by chloride stress corrosion cracking or Cl-SCC is valves, fittings, and flanges. Description: critical in controlling process flow, these parts are often subjected to tensile stresses due to operational pressures. Valves, fittings, and flanges details: welded or threaded joints, susceptible to crack initiation. Impact: loss of containment and process integrity. Number 8 of the units or equipment affected by chloride stress corrosion cracking or Cl-SCC is welded structures. Description: welded zones are particularly vulnerable due to residual stresses and microstructural changes. Welded structures details: weld metal and heat-affected zones or HAZ, prone to SCC in chloride environments. Examples: structural steel welds, stainless steel welds in chemical plants. Number 9 of the units or equipment affected by chloride stress corrosion cracking or Cl-SCC is storage tanks. Description: tanks storing chloride-rich chemicals or seawater. Storage tanks details: metallic tanks, especially those made of susceptible steels. Risks: cracks lead to leaks, environmental contamination, and safety hazards. Number 10 is other equipment and structural components affected by chloride stress corrosion cracking or Cl-SCC. Boilers and condensers, sometimes affected if chlorides concentrate in feedwater. Desalination units, components exposed to brine and seawater. Cooling towers, metal parts subjected to chloride-laden water spray or immersion. Chloride stress corrosion cracking compromises a broad spectrum of industrial equipment and structural units, especially those exposed to chloride-rich environments under tensile stress. The most vulnerable areas include welded joints, bends, and stressed components made of susceptible materials like austenitic stainless steels and high-strength steels. Preventing Cl-SCC in these units involves material selection, controlling residual and operational stresses, implementing corrosion protection. Appearance or morphology of chloride stress corrosion cracking damage based on API 571. Number A, surface breaking cracks can occur from the process side or externally under insulation. See Figure 4-133, external cracking of Type 304 SS instrument tubing under insulation. See Figure 4-134, external cracking of Type 304 SS instrument tubing under insulation. Number B, the material usually shows no visible signs of corrosion. Number C, characteristic stress corrosion cracks have many branches and may be visually detectable by a cracked appearance of the surface. See Figure 4-135, cracking on the shell side of Type 316 LSS tubes in steam service at 450 degrees Fahrenheit or 232 degrees Celsius, showing tubes after PT inspection. The cracks can be seen in the center tube, arrow. See Figure 4-136. Close-up of the tube in Figure 4-135 showing tight cracks with a spider web appearance. Number D, metallography of cracked samples typically shows branched transgranular cracks. See Figure 4-137, photomicrograph of a cross-section of sample in Figure 4-136 showing fine branching cracks. Unetched, Mag. 50X. See Figure 4-138. Another photomicrograph of a cross-section of a cracked tube illustrating the transgranular mode of cracking initiating on the surface. Etched. See Figure 4-139, chloride SCC on the thread surface of a failed 303 SS bolt. Number E, sometimes intergranular cracking of sensitized 300 series SS may also be seen. Number F, welds in 300 series SS usually contain some ferrite, producing a duplex structure that is usually more resistant to Cl-SCC. Number G, corrosion-resistant nickel-based alloys are also susceptible to cracking under severe conditions. See Figure 4-140, severe cracking of a finned alloy C276 tube in a dethanizer reboiler after 8 years service due to ammonium chloride carryover, as showing in Figure A, hundreds of cracks initiated on the OD process side of the tube associated with the cold-worked portion of the tube at the fins as showing in Figure B, branching transgranular cracks as showing in Figure C. Number H, fracture surfaces often have a brittle appearance. Here's a detailed explanation of the appearance and morphology of chloride stress corrosion cracking or Cl-SCC damage. Overview. The physical manifestation of Cl-SCC is characterized by distinctive crack features and surface features that reveal the underlying corrosion mechanisms. Recognizing these morphological signs is crucial for diagnosis, failure analysis, and implementing preventative measures. The appearance and morphology of chloride stress corrosion cracking or Cl-SCC damage. Number 1 is general morphology of Cl-SCC. Type of this damage: Cl-SCC manifests as intergranular or transgranular cracks that are often interconnected and branching. These cracks can be long and narrow, sometimes extending over a significant length, or short and localized. Cl-SCC crack appearance includes fine, hairline cracks, usually less than 0.1 mm wide, depth. Cracks can penetrate deeply into the material, often several millimeters, depending on stress and environmental conditions. Length ranges from microscale to several centimeters, sometimes propagating along grain boundaries or through grains. Number 2 of the appearance and morphology of chloride stress corrosion cracking or Cl-SCC damage is surface features and morphology. Number A, surface roughness. Cracked areas often exhibit increased roughness compared to the surrounding material. Surface may show striations or rough, jagged edges along crack paths. Number B of surface features and morphology is localized pitting and voids. Prior to crack initiation, chloride-induced pitting corrosion may be observed. Fresh cracks often begin at or near pits or microvoids. Number C of surface features and morphology is blistering or delamination. In some cases, chloride attack induces localized spalling or delamination at the surface due to subsurface crack growth. Number 3 of the appearance and morphology of chloride stress corrosion cracking or Cl-SCC damage is crack path and mode of propagation. Number A, intergranular versus transgranular. Intergranular SCC, cracks follow grain boundaries, appearing as parallel lines along the grain edges. This is typical in sensitized stainless steels. Transgranular SCC, cracks cut through grains, appearing as rough, faceted features crossing grain interiors. Number B of crack morphology are intergranular cracks tend to be smooth, planar, and follow the grain boundary network. And transgranular cracks show step-like or faceted morphology, often with jagged edges. Number C of crack path and mode of propagation is branching and T-junctions. Cracks may branch or intersect, forming complex networks, sometimes resembling filamentary or web-like patterns. Number 4 of the appearance and morphology of chloride stress corrosion cracking or Cl-SCC damage is subsurface features. Number A, subsurface crack growth. Cracks often initiate at the surface and grow inward, sometimes creating subsurface cavities or voids. These cavities can coalesce, resulting in microstructural damage. Number B of subsurface features is corrosion products. Fine corrosion products, such as chlorides, oxides, may be present within cracks or on the surface. These often appear as white, crusty deposits or rust-like layers depending on the material. Number 5 of the appearance and morphology of chloride stress corrosion cracking or Cl-SCC damage is fractography and microstructure. Number A, fracture surface features, beach markings or striations, indicate cyclic crack growth. Faceted surfaces, result from transgranular fracture. Intergranular cracks, show smooth, planar features with possible corrosion deposits along grain boundaries. Number B of fractography and microstructure is microstructural observations, grain boundary attack, visible as corrosion along grain boundaries. Microvoids, small voids or microcracks may be present at the crack tips. Number 6 of the appearance and morphology of chloride stress corrosion cracking or Cl-SCC damage is visual and microscopic examination. Number A, macroscopic inspection. Cracks are often visible as hairline or narrow lines on the surface. Surface discoloration may be apparent if corrosion products have accumulated. Number B of visual and microscopic examination is microscopic inspection. SEM or scanning electron microscopy reveals detailed crack morphology, including step-like features, facets, and grain boundary corrosion. Light microscopy can show the intergranular or transgranular nature and microvoids. Cl-SCC typically manifests as long, narrow, and often branching cracks that follow grain boundaries, intergranular, or cut through grains, transgranular. The surface appearance includes hairline cracks, rough, jagged edges, and localized corrosion deposits. The morphology is influenced by the microstructure, material susceptibility, and environmental conditions. Identifying these features through visual, microscopic, and fractographic analysis is essential for diagnosing Cl-SCC damage, understanding its mechanisms, and preventing future occurrences. Chloride stress corrosion cracking Cl-SCC damage prevention and mitigation based on API 571. Number A, use resistant materials of construction. Number B, when hydrotesting, use low chloride content water and dry out thoroughly and quickly. Number C, properly applied coatings under insulation. Number D, avoid designs that allow stagnant regions where chlorides can concentrate or deposit. Number E, a high-temperature stress relief of 300 series SS after fabrication may reduce residual stresses. However, consideration should be given to the possible effects of sensitization that may occur, increasing susceptibility to polythionic SCC, possible distortion problems and potential reheat cracking. Here is a comprehensive, detailed explanation of prevention and mitigation strategies for chloride stress corrosion cracking or Cl-SCC. Overview: Cl-SCC is a complex failure mechanism influenced by material susceptibility, environmental conditions, residual and operational stresses. Effective prevention and mitigation require an integrated approach involving material selection, design practices, environmental control, and ongoing inspection. Prevention and mitigation strategies for chloride stress corrosion cracking or Cl-SCC. Number 1 is material selection. Use of resistant materials, corrosion-resistant alloys or CRA. Select materials inherently resistant to chloride environments, such as tantalum, titanium, or nickel-based alloys. Use of stainless steel grades. Use highly stabilized or low susceptibility stainless steels, such as duplex, super-austenitic, or nickel alloys like Inconel, instead of susceptible grades like 304 or 316 if chloride exposure is severe. Use of avoid sensitized materials. Prevent use of materials prone to sensitization, such as certain stainless steels in specific heat treatments, that develop chromium carbide precipitates at grain boundaries, increasing intergranular SCC susceptibility. In material selection, use of microstructural control method. Refined grain size. Fine-grained microstructures are less susceptible to intergranular attack. Heat treatment. Proper annealing and solution treatment to minimize residual stresses and prevent sensitization. Number 2 of prevention and mitigation strategies for chloride stress corrosion cracking or Cl-SCC is design considerations. Number A, reduce stress concentrations. Design for low residual stress. Use smooth welds, avoid sharp corners, and ensure proper welding procedures to minimize residual tensile stresses. Avoid overstressing. Ensure operational stresses stay well below the material's stress corrosion threshold. Number B, of design considerations is incorporate stress relief features. Stress relief post-welding. Use techniques like stress relief annealing to reduce residual stresses in welded structures. Design for ease of inspection. Include access points and features allowing regular inspection and maintenance. Number 3 of prevention and mitigation strategies for chloride stress corrosion cracking or Cl-SCC is environmental control. Number A, chloride level management, includes, control chloride exposure, minimize chloride concentrations by, using deionized or low chloride water in cooling and process streams, avoiding seawater or salt-laden environments where possible. And chloride level management by corrosion inhibitors. Apply chloride scavengers or corrosion inhibitors suitable for the specific environment. Number B, of environmental control is pH control. Maintain optimal pH, keep pH at levels that reduce chloride ion activity. Slightly alkaline conditions are generally less aggressive. Number C, of environmental control is coatings and barriers. Protective coatings. Apply corrosion-resistant coatings or linings, such as epoxy, rubber lining, to prevent chloride ingress. Cathodic protection. Use impressed current or sacrificial anodes to reduce active corrosion potential. Number 4 of prevention and mitigation strategies for chloride stress corrosion cracking or Cl-SCC is operational strategies. Number A, stress management. Reduce applied stresses. Minimize tensile stresses during operation through proper design and load management. Limit start-stop cycles. Reduce cyclic stresses that can accelerate crack initiation. Number B, of operational strategies is controlled maintenance. Regular inspections. Use non-destructive testing, NDT, techniques like ultrasonic testing, eddy current, or dye-penetrant testing to detect early cracks. Cleaning. Remove chloride deposits and corrosion products from surfaces regularly to inhibit crack initiation. Number 5 of prevention and mitigation strategies for chloride stress corrosion cracking or Cl-SCC is inspection and monitoring. Number A, routine inspection, visual inspection, regularly check for cracks, surface discoloration, or pitting. Advanced NDT, implement ultrasonic testing, radiography, or phased array ultrasound to detect subsurface cracks. Number B, of inspection and monitoring is condition monitoring, corrosion coupons and probes, use in situ sensors to monitor chloride activity and corrosion potential, structural health monitoring, deploy strain gauges or acoustic emission sensors to detect crack growth. Number 6 of prevention and mitigation strategies for chloride stress corrosion cracking or Cl-SCC is repair and replacement. Number A, crack repair, welding repairs, remove cracks via grinding or welding, followed by proper heat treatment, use of inhibitors, apply corrosion inhibitors post-repair to prevent reinitiation. Component replacement, when damage is extensive or highly susceptible materials are compromised, replace with more resistant materials or redesign. Prevention of Cl-SCC is most effective when a comprehensive approach is adopted, combining material science, engineering design, environmental management, and vigilant maintenance. Recognizing the specific environment and operational conditions is essential for tailoring these strategies effectively. Chloride stress corrosion cracking or Cl-SCC inspection and monitoring based on API 571. Number A, cracking is surface connected and may be detected visually in some cases. Number B, PT or phase analysis EC techniques are the preferred methods. Number C, eddy current inspection methods have also been used on condenser tubes as well as piping and pressure vessels. Number D, extremely fine cracks may be difficult to find with PT, special surface preparation methods, including polishing or high-pressure water blast, may be required in some cases, especially in high-pressure services. Number E, UT. Number F, often, RT is not sufficiently sensitive to detect cracks except in advanced stages where a significant network of cracks has developed. Here's a detailed overview of inspection and monitoring methods used to detect chloride stress corrosion cracking or Cl-SCC damage overview. Detecting chloride-induced stress corrosion cracking early is crucial to prevent catastrophic failure. Since SCC often initiates internally or subsurface and progresses gradually, a combination of inspection techniques and monitoring systems is employed for early detection, assessment, and ongoing surveillance. Here's a detailed overview of inspection and monitoring methods used to detect chloride stress corrosion cracking or Cl-SCC damage. Number 1 is visual inspection. Description: the most basic and routine method, involves examining accessible surfaces for signs of damage such as cracks, discoloration, pitting, or corrosion products. Visual inspection details: surface cracks, hairline or widened cracks, especially near welds or areas with residual stresses, discoloration or rust, can indicate corrosion activity. Limitations: cannot reliably detect subsurface or internal cracks, surface access is required. Number 2 of inspection and monitoring methods used to detect chloride stress corrosion cracking is Cl-SCC damage is liquid penetrant testing or LPT. Description of liquid penetrant testing is, uses a penetrant dye applied to the surface to reveal surface breaking cracks. Process of liquid penetrant testing includes, clean the surface thoroughly, apply penetrant dye and allow it to seep into cracks. Remove excess dye, apply a developer to draw out the dye from cracks, making them visible under UV or white light. Advantages of liquid penetrant testing are, sensitive to surface breaking cracks, relatively simple and quick, and limitations of liquid penetrant testing are, cannot detect subsurface cracks, requires clean, smooth surfaces. Number 3 of inspection and monitoring methods used to detect chloride stress corrosion cracking is Cl-SCC damage is magnetic particle testing or MPT. Description of MPT, suitable for ferromagnetic materials to detect surface and near-surface cracks. Process of magnetic particle testing: magnetize the component, apply magnetic particles, wet or dry. Cracks disturb the magnetic field, attracting particles and revealing defect locations. Advantages of magnetic particle testing are, good for detecting surface and shallow subsurface cracks, portable and rapid, and limitations of magnetic particle testing are, only applicable to ferromagnetic materials, less effective for deep cracks. Number 4 of inspection and monitoring methods used to detect chloride stress corrosion cracking is Cl-SCC damage is ultrasonic testing or UT. Description of UT, uses high-frequency sound waves to detect internal cracks and flaws. Types of ultrasonic testing, pulse echo method, sends ultrasonic pulses into the material, reflections indicate flaws. Phased array ultrasonic testing, provides detailed imaging of internal features. Application of ultrasonic testing R, detects internal or subsurface cracks characteristic of SCC, capable of measuring crack depth and size. Advantages of ultrasonic testing are, detects subsurface cracks, quantitative assessment, and limitations of ultrasonic testing are, requires skilled operators, surface roughness and geometry can affect signal quality. Number 5 of inspection and monitoring methods used to detect chloride stress corrosion cracking is Cl-SCC damage is radiographic testing or RT. Description of radiographic testing, uses X-rays or gamma rays to produce images of internal structures. Application of radiographic testing, visualize internal cracks, voids, or corrosion products. Suitable for inspecting welds and complex geometries. Advantages of radiographic testing are, provides detailed internal images, detects internal cracks and corrosion, and limitations of radiographic testing are, expensive and requires specialized equipment, less effective for very small or fine cracks. Number 6 of inspection and monitoring methods used to detect chloride stress corrosion cracking is Cl-SCC damage is eddy current testing or ECT. Description of eddy current testing, non-contact electromagnetic method sensitive to surface and near-surface flaws. Application of eddy current testing, detects surface cracks and corrosion, suitable for inspecting conductive materials like stainless steel. Advantages of eddy current testing are, rapid and portable, no need for surface cleaning, and limitations of eddy current testing are, limited depth penetration, less effective on complex geometries. Number 7 of inspection and monitoring methods used to detect chloride stress corrosion cracking is Cl-SCC damage is acoustic emission or AE monitoring. Description of acoustic emission monitoring, detects transient elastic waves produced by crack initiation and growth. Application of acoustic emission monitoring, continuous monitoring during operation. Useful for early detection of active cracking. Advantages of acoustic emission monitoring are, can monitor large structures in real time, detects active crack growth, and limitations of acoustic emission monitoring are, requires specialized sensors and analysis, may produce false positives from other sources. Number 8 of inspection and monitoring methods used to detect chloride stress corrosion cracking is Cl-SCC damage is corrosion monitoring techniques. Number A, electrochemical sensors and probes. Detect changes in corrosion potential or current indicative of chloride activity. Examples, corrosion potential probes, linear polarization resistance, LPR, probes. Number B, chloride ion selective electrodes. Measure chloride ion activity directly. Number C, corrosion coupons. Expose metal samples in service environments to monitor corrosion rates over time. Number 9 of inspection and monitoring methods used to detect chloride stress corrosion cracking is Cl-SCC damage is advanced non-destructive evaluation or NDE technologies. Number A, infrared thermography, detects temperature variations caused by crack-related corrosion activity. Number B, fiber optic sensors, embedded sensors can detect strain and crack growth in real time. Number C, digital image correlation or DIC, uses high-resolution cameras to monitor surface deformation and crack propagation. Number 10 of inspection and monitoring methods used to detect chloride stress corrosion cracking is Cl-SCC damage is structural health monitoring or SHM. Description, integration of sensors into structures for continuous or periodic monitoring. Components, strain gauges, acoustic sensors, corrosion sensors, and wireless data acquisition systems. Advantages, early detection of crack initiation and growth, enables predictive maintenance. Combination of methods provides the best coverage for early detection. Routine inspections should be scheduled based on service environment, material susceptibility, and operational history. Monitoring systems enable proactive maintenance and extend service life. Thank you.